The ground beneath your feet is not the most fundamental thing holding you up. Beneath the soil, there is rock. Beneath the rock, there is mantle. Beneath the mantle, there is a molten core turning slowly in the dark. And beneath all of that, beneath matter itself, there is something that physicists call a field. A field that fills every cubic centimeter of space in the known universe. A field that has no color, no smell, no texture. A field you cannot touch and cannot see. It is called the Higgs field. The Higgs field is not a metaphor. It is not a convenient mathematical shorthand for something we do not yet understand.
It is a real, physical entity. A quantum field that permeates all of space, the way water permeates a saturated sponge. And right now, at this moment, while you breathe and the earth turns and distant stars collapse into themselves, that field is sitting at a particular value. A precise, specific value. A number. That number is not arbitrary. It determines everything. When physicists speak of a field having a value, they mean something a little like temperature, a number assigned to every point in space. But unlike temperature, the value of the Higgs field is not something you can measure with a thermometer or feel with your hand. Its effects are far more fundamental than warmth or cold. The mass of the electron. The mass of the top quark. The mass of the W and Z bosons that carry the weak nuclear force. Every particle that has mass acquires it by interacting with the Higgs field, and the strength of that interaction depends entirely on the value the field currently holds. Change that value, and you change the mass of every particle in the universe. Change the mass of every particle, and you change the strength of every force. Change every force, and chemistry fails. Atoms as we know them dissolve into something unrecognizable. Stars cannot ignite. DNA cannot fold. Neurons cannot fire. Think of the Higgs field as the operating system of physics.
Every law you have ever trusted, the laws that keep your chair solid beneath you, that keep the sun burning at a distance precisely right for liquid water, that allow the carbon in your body to bond into the long organic chains that make life possible. Every one of those laws runs on top of the Higgs field's current value. The laws are not written into the fabric of the universe as permanent axioms. They are outputs. They are consequences. They depend on a number that is right now sitting quietly at a particular value throughout all of space, like a tuning fork struck at the moment of the Big Bang and still vibrating, perfectly, 13.8 billion years later.
And that number could, in principle, be different. This is the thing that physicists discuss in careful language at conferences and in papers, full of Greek symbols and renormalization corrections. Beneath all the careful language, the idea is staggering. The physical constants that make our universe habitable, that make our universe exist in any recognizable form, are not guaranteed. They are not eternal axioms carved into the structure of reality before time began. They are, in the deepest possible sense, contingent. They happen to be what they are because the Higgs field happens to sit where it sits. This is different from saying that the laws of physics could have been different in some vague philosophical way. This is not speculation about other possible universes or alternative histories.
This is saying something more immediate. The laws of physics that hold right now, in this universe, at this moment, depend on the current state of a real physical field that obeys real physical equations. And those equations allow the field to change state. The field has a potential energy, a relationship between its value and its energy, like the relationship between the height of a ball and its gravitational potential energy. A ball placed somewhere on a hillside will roll downhill if the slope allows it. A quantum field sitting at a particular value will evolve toward lower energy states if the potential permits it. The question is the shape of the potential.
The question is whether the current value of the Higgs field sits at the true bottom of its energy landscape, or only at a local minimum, a valley that feels like the bottom but is not. Philosophers have argued for centuries about whether the universe had to be this way, whether the constants of nature are necessary or contingent, whether a god or a deeper mathematical principle fixes them, whether anything could have been otherwise. Physicists have now found a more disturbing version of that question. The universe may not have had to be this way, and it may not stay this way. The Higgs field, sitting at its current value, is like a ball resting in a valley. The ball is still. It appears stable. It appears permanent.
You could watch it for 1 billion years and see no movement. But whether that valley is the deepest valley in the entire landscape, whether there is another valley somewhere, lower down, separated from this one by a slope the ball cannot climb through ordinary means, that is a question we have not yet answered with certainty. The ground beneath physics may be the true ground, or it may be a ledge. And the difference between those two possibilities is the difference between a universe that will exist in something like its current form for as long as time allows, and a universe that is waiting, in every cubic centimeter of space, for the moment when quantum mechanics decides to reach through the barrier and let it fall.
There is a strange intimacy in this idea. The Higgs field is not some distant phenomenon, localized to a laboratory or a distant star. It is here, in this room, filling the space between every atom in your body and every atom in the air around you. You have been immersed in it your entire life without knowing it. Every electron in every atom of every molecule of the food you ate, the air you breathed, the thoughts that have moved through your nervous system, all of it exists because the Higgs field is what it is, here, now, in this moment. The Higgs field is not something physics tells us about from a distance. It is the medium we live in.
It is, in a sense, more literal than most metaphors allow, the substance of physical reality itself. The reason particles have mass, the reason atoms can form, the reason the complexity of chemistry is possible at all, it traces back to a field sitting quietly at a particular value, everywhere, all at once. That value has not changed detectably in 4 billion years of Earth's history, in 13.8 billion years of the universe's existence. By every measurement we can make, it is holding. The floor is solid. Nothing suggests an imminent change. The question physicists are raising is not about tomorrow or next year or the next billion years.
The question is about the deep structure of the thing itself. Whether the stability we observe is the stability of bedrock, or the stability of a very still lake sitting just above a fault line. We do not know which it is. The mathematics does not yet give us a definitive answer. And that uncertainty, quiet as it is, sits at the foundation of everything we think we know about physical reality.
In quantum field theory, the state of lowest possible energy is called the vacuum. The word is misleading. This is not the vacuum of empty space, not merely the absence of matter, the void between atoms, or the near-nothingness between galaxies. The vacuum, in this technical sense, is the ground state of a quantum field, the configuration in which the field has settled after releasing all the energy it can. It is the floor beneath everything else, the state from which no further energy can be extracted. But the energy landscape of a quantum field can be complicated. It can have multiple valleys.
A field can settle into a local minimum, a point that is the lowest energy in its immediate neighborhood, without being the lowest energy state overall. This is called a metastable vacuum. It is stable in the sense that small, ordinary perturbations cannot dislodge it, but it is not truly globally stable. There is a lower state available somewhere else in the landscape. The field simply lacks the energy to climb the slope and reach it through classical means. Imagine a marble sitting in a shallow bowl on top of a table. The marble is stable within the bowl. Small nudges send it rolling a little and then back to the center. It looks like it has found its resting place.
But the table has a ledge, and beyond the ledge the floor is much lower. The marble is in a local minimum, not a global one. Its apparent stability is real, but it is not ultimate. The Higgs field may be that marble. In 2012, physicists at CERN announced the discovery of the Higgs boson, the particle associated with the Higgs field, the quantum ripple that the field produces when struck with sufficient energy. Its mass was measured at 125.25 billion electron volts. The discovery was celebrated worldwide, and rightly so. It completed the standard model of particle physics, the most precisely tested theory in the history of science. Champagne was opened.
Peter Higgs, then 83 years old, was photographed with tears in his eyes. But among the congratulations, a quieter conversation was beginning. The stability of the Higgs vacuum depends critically on the Higgs boson's own mass. This sounds circular, but it reflects a deep feature of quantum field theory. The Higgs field's potential, the shape of its energy landscape, is not fixed by classical physics. It is corrected at every energy scale by quantum contributions from every other particle it couples to. The top quark, in particular, is very heavy and couples strongly to the Higgs field, and its quantum corrections tend to bend the potential downward at high field values, tilting the landscape away from stability. When you feed the measured value of the Higgs boson mass, 125.25 billion electron volts, into the calculations, and you run the equations forward to very high energies, you find that the Higgs potential develops a second minimum. A deeper valley, far from where the field currently sits, at field values many orders of magnitude larger than the current vacuum value. A true vacuum, lower in energy, separated from our current vacuum by a barrier. A paper by Butazzo and collaborators, published in 2013, performed this calculation with careful precision, accounting for quantum corrections from all known particles in the standard model. Their conclusion was phrased with the restraint that physicists prefer, but the content was not restrained.
The universe appears, on the best current measurements, to lie in a metastable region, the false vacuum, rather than the stable region. The central values of the measured parameters point to metastability. The error bars are large enough to allow for full stability, and they are large enough to allow for outright instability. But the most probable reading of what we know places our universe in a false vacuum. Not certainly, but probably. This is worth sitting with for a moment. The measurements made at CERN, the most powerful particle accelerator ever built by human civilization, using decades of accumulated theoretical knowledge and some of the most precise experimental equipment ever constructed. Those measurements suggest that the universe we inhabit is not in its lowest energy state.
Not beneath the apparent solidity of physical law, there is a deeper, more fundamental configuration that the universe could adopt. That we are, in the vocabulary of theoretical physics, in a false vacuum. A local minimum, a temporary equilibrium. The true vacuum, if it exists, has lower energy. The true vacuum is deeper in the landscape. And in quantum mechanics, a system in a metastable state does not stay there forever. It cannot. Quantum mechanics has a mechanism, a universal mechanism, by which barriers that cannot be crossed classically can nevertheless be crossed. Given enough time, or enough space, or both, any metastable system will eventually make the transition. We exist in a valley. Every feature of physical reality, the periodic table, the way light bends, the spin of electrons, the lifetime of a proton, emerges from the specific shape of this valley. And the mathematics that describes our universe contains, implicit in its own structure, the possibility of a different valley. Darker, deeper, determined by different numbers. A valley in which none of what we are is possible. The philosopher Sidney Coleman did not use the word haunting in his papers. He used Lagrangians and path integrals and dimensional regularization. But the picture his mathematics described was haunting nonetheless. A universe that carries within its own field equations the seed of its own replacement.
A physical reality that is stable enough for stars to form, and life to evolve and civilizations to rise, but not stable enough, in the deepest mathematical sense, to last forever. Not stable enough to be final. We exist in a universe that may be waiting to become something else. This is the feature of the Higgs discovery that tends to go unreported. The headlines in 2012 said, "Particle found, theory confirmed, standard model complete." All of that is true, but the standard model, now complete with the Higgs mass measured, makes a prediction about the universe that goes beyond particle physics. It makes a prediction about the nature of the ground beneath physics itself, and that prediction is not reassuring.
The measured Higgs mass, combined with the measured top quark mass, places the universe's vacuum state in a region of the theoretical parameter space that physicists label with the word metastable, not with the word stable, not with the word safe. Metastable, meaning it is the lowest state locally, but perhaps not globally, meaning it is stable against small disturbances, but not against the specific mechanism of quantum tunneling, given infinite time. We cannot increase the precision of the measurement by running the experiment again. The uncertainty in the top quark mass, determined by the way quarks interact at high energies, through quantum chromodynamic corrections that are notoriously difficult to calculate, means that the stability question may remain unresolved for decades, or perhaps longer.
Resolving it may require a particle accelerator far beyond anything currently planned. The kind of machine that would cost more than any scientific instrument ever built by humans, that would take a generation to construct, that might not produce results within the lifetime of anyone alive today. And in the meantime, the universe continues. The field holds its value. The ball sits in its bowl. Whether the ledge beyond the bowl leads to a gentle slope or a sheer drop, we cannot yet say.
Classical physics respects barriers. In the classical world, an object with insufficient energy to cross a hill cannot cross the hill. It reaches the slope, slows, stops, and slides back. The barrier is a wall, and the wall is absolute. This is intuitive. It matches everything we observe at human scales. A ball rolled toward a rise will go only as far as its kinetic energy allows, and no further. No exceptions. Quantum mechanics does not respect this. At the quantum scale, particles are not points moving along definite trajectories. They are described by wave functions, extended probability distributions that specify, for each point in space, the likelihood of finding the particle there. The wave function does not stop abruptly at the classical turning point.
It decays exponentially into the forbidden region, the region beyond the barrier, but it does not go to zero. There is always a small but non-zero probability amplitude for the particle to be found on the other side of a barrier it classically could never cross. This is quantum tunneling. It is not theoretical conjecture. It is measured, demonstrated, built upon. Tunneling is the mechanism by which hydrogen nuclei in the sun's core manage to fuse at temperatures that classical physics says should be insufficient. The thermal energies of protons in the sun are too low, by a factor of 1,000 or more, to overcome the electrostatic repulsion between them classically. Tunneling closes the gap. Without quantum tunneling, the sun would not burn. Without quantum tunneling, there would be no light on Earth, no photosynthesis, no food chain, no us. Tunneling is also why certain radioactive nuclei decay. The alpha particle inside a nucleus does not have enough energy to escape the nuclear potential well by going over the barrier. It tunnels through. The rate at which it does so depends on the width and height of the barrier, which is why some isotopes have half-lives of billions of years and others of microseconds. The mathematics is well understood. The phenomenon is real. And tunneling applies not just to particles, but to quantum fields. A quantum field sitting in a metastable vacuum is, at bottom, a quantum system with an energy landscape that has a barrier.
The field's configuration, its value at every point in space, is not fixed with perfect rigidity. Quantum fluctuations constantly ripple through the field, creating momentary deviations from the vacuum value at every location. Most of these fluctuations are small and short-lived, and the field returns to its resting state. But occasionally, a fluctuation in a small region of space will be large enough in the right direction to begin the process of tunneling through the potential barrier to the true vacuum on the other side. Coleman and DeLucia worked out the mathematics of this in 1980.
Their calculation described the probability that a small, approximately spherical region of space would spontaneously nucleate in the true vacuum. Tunneling through the barrier collectively as a coherent field configuration rather than as individual particles.
They call this a bubble of true vacuum. The probability per unit volume per unit time, the rate at which a bubble might spontaneously appear in any given cubic meter of space in any given second, is extraordinarily small. For plausible values of the parameters that describe the Standard Model, this rate is suppressed by factors that would be written as 10 raised to powers in the hundreds. 10 to the negative 300, 10 to the negative 400. Numbers so small they have no analogy in ordinary experience.
The number of atoms in the observable universe is approximately 10 to the 80. The number of seconds since the Big Bang is roughly 430 trillion, about 4 times 10 to the 17. Even multiplying every atom by every second gives you only about 10 to the 97. Against a probability of 10 to the negative 400, that is still negligible. And yet, the universe is not just the observable universe. The observable universe, the sphere of space from which light has had time to reach us in 13.8 billion years, is bounded by our cosmic horizon. But the universe itself, almost certainly, extends far beyond that horizon.
Inflationary cosmology suggests that the total volume of space may be incomprehensibly larger than what we can see. Some models suggest it is effectively infinite. If the universe is infinite, then every non-zero probability, however small, occurs infinitely many times. The tunneling event has not merely happened somewhere. It has happened infinitely often. Even setting aside infinity, consider the timescales involved. The sun will burn for another 5 billion years. The universe, in the absence of vacuum decay, would continue for timescales measured in 10 to the 100 years or more before entropy finally claims the last cold remnants of matter. Over those timescales, even extraordinarily suppressed tunneling rates begin to accumulate into a non-trivial probability of at least one nucleation event somewhere in the volume of space.
Krauss and Dent, in 2008, noted something subtle about this calculation. The tunneling rate is not simply a fixed number. It depends on the history of the universe, on whether de Sitter expansion has effectively isolated different regions of space from one another. Their paper raised the possibility that the calculation of vacuum lifetime is more complex than Coleman's original treatment suggested, and that in certain regimes, the effective rate could be different from naive estimates. The details remain an active area of research. The uncertainty cuts both ways. The true rate might be lower than estimated, or it might be higher. What is not uncertain is the principle. A metastable quantum field will eventually tunnel. The only question is when.
And the only honest answer is, we do not know. The tunneling rate depends on parameters we have not measured with sufficient precision. The Higgs boson mass and the top quark mass, both measured but with finite experimental uncertainty, push the tunneling rate up or down by many orders of magnitude depending on their exact values. The lifetime of our vacuum, if it is indeed a false vacuum, could be 10 to the 60 years, or 10 to the 600 years, or anywhere in between. What this means is that we cannot rule out a tunneling event having already occurred. Not here, not in our observable patch of space. We would know about that in the most final possible way. But somewhere beyond our cosmic horizon.
Somewhere in the vast volume of space that we cannot observe and from which we can receive no signal, in that region perhaps, a bubble has already formed, is already growing. Low probability, is not the same as impossibility, and the universe has given this event a very long time and a very large arena in which to play out. Time is the most patient force in existence. It does not hurry. It simply accumulates. And in its accumulation, it transforms the nearly impossible into the inevitable. There is something philosophically unsettling about this particular kind of inevitability. It is not the inevitability of entropy, the slow, grinding dispersal of order into disorder that thermodynamics promises over vast timescales. Entropy is a gradual process.
Its effects accumulate slowly, allowing complexity to flourish for billions of years before the final cold and silence arrives. The inevitability of quantum tunneling, if the vacuum is indeed metastable, is different in kind. It is punctual. It happens all at once, at a specific moment, at a specific location. It does not erode. It does not warn. It simply occurs. And the probability of it occurring somewhere in the universe's history, somewhere in the vast volume of space that may extend far beyond what we can observe, that probability over the timescales involved is not negligible in any meaningful sense. The universe is old. The universe may be vast beyond imagination, and every moment of its existence, in every region of its volume, the quantum field is fluctuating.
Testing, in a sense, the boundary between the false vacuum and the true, finding over and over that the barrier holds, until, perhaps, once, somewhere, it does not.
In the Coleman-de calculation, the tunneling event does not produce a particle or a pulse of radiation. It produces a bubble, a sphere of true vacuum nucleating at a point in space. Inside this sphere, the Higgs field has crossed the potential barrier and settled into its lower energy state. The field value inside is different from the field value outside. At the boundary, the bubble wall, the field transitions rapidly from one value to the other across a thickness that, depending on the specific physics, might be smaller than a proton. And that wall does not stay still. The energy released by the transition from false vacuum to true vacuum, the energy difference between the two states, is pumped into the bubble wall. The wall gains kinetic energy. It accelerates outward. The acceleration continues as the bubble grows, because at every new radius, fresh false vacuum is being converted to true vacuum, releasing more energy, driving the wall faster. The wall approaches the speed of light asymptotically, and within a cosmologically negligible time after nucleation, it is moving at a speed indistinguishable from the speed of light in all outward directions. The speed of light is not merely fast. The speed of light is the speed of causality itself. It is the rate at which cause and effect propagate through space. It is the fundamental limit built into the geometry of space-time.
When an object moves at the speed of light, it is not racing against the universe's communication network. It is traveling at exactly the same speed as that network. This is what separates vacuum decay from every other catastrophe physicists have ever contemplated. A supernova releases an expanding shell of high-energy particles and light. It is devastating to anything nearby.
but the light from the supernova arrives before the destructive material, and at sufficient distance, an observer would see the flash and have time, minutes, hours, to understand what was coming. A gamma-ray burst, the most energetic electromagnetic event known, travels at the speed of light.
But a gamma-ray burst is collimated. It fires in two narrow jets from the poles of a collapsed star, and only matter lying directly in the path of those jets is affected. A nearby black hole would first make its presence known through gravitational perturbations that could be detected years or decades before any danger arrived. The vacuum decay bubble is none of these things. It is a sphere. It expands in every direction simultaneously. It travels at the speed of light, which means no physical process can send a signal ahead of it. There is no precursor, no shadow, no warning. The first indication that the bubble wall has arrived is the arrival of the bubble wall. And at that point, the warning is simultaneous with the event.
There is no interval between the two. Inside the bubble, the value of the Higgs field is different. We cannot say exactly how different, because we do not know the precise location of the true vacuum. But we can say with confidence that it is not merely a small perturbation from the current value. A true vacuum, if it exists below our current false vacuum with a significant energy gap, almost certainly has a Higgs field value very different from today's. Potentially many orders of magnitude larger, or in a completely different region of field space. The physical laws inside the bubble would not be a modified version of our physics. They would be different physics. The mass of the electron would be different.
The mass of quarks, the fundamental constituents of protons and neutrons, would be different. The coupling constants that govern the electromagnetic force, the weak force, and the strong nuclear force would be different. This is not speculation. These quantities are determined by the structure of the Standard Model and its relationship to the Higgs field. Change the Higgs field value, and you change all of them simultaneously everywhere inside the bubble. Inside the bubble, protons may not be stable. The proton's stability in our current universe is a consequence of a specific balance between the masses of the quarks it contains and the forces that bind them. In the true vacuum, that balance would be different.
Quarks might combine into entirely different bound states, or might not form stable bound states at all. A proton crossing the bubble wall would not explode or melt. It would simply cease to meet the conditions for being a proton. The quarks inside it would experience different forces, acquire different effective masses, and whatever they became in the true vacuum would bear no resemblance to the matter we know. Consider what you are made of. Your body contains roughly 7 × 10⁻27 atoms. Each atom has a nucleus. Protons and neutrons bound by the strong force, with the number of protons determining which element it is.
Around that nucleus, electrons orbit at distances determined by the electromagnetic force and the quantum mechanical constraints imposed by the electron's mass and spin. Every molecule in every cell of your body is a specific arrangement of atoms held together by electromagnetic bonds whose properties follow precisely from the physical constants determined by the Higgs field's current value. The bubble wall would cross your position in space at the speed of light. A neural signal travels at roughly 100 meters per second. The bubble wall would arrive approximately 10 million times faster than the fastest signal your nervous system could generate. There would be no sensation. There would be no experience of transition.
The physical substrate required for experience, atoms, molecules, neurons, chemistry, would cease to conform to the laws that make those things possible, faster than any process in your body could register that anything had happened. There would be no moment of realization, no final thought. Not because death would be painless. Pain requires a nervous system, and a nervous system requires physics that would no longer apply. But because the concept of experience requires a physical substrate that would no longer exist in any form we recognize. The bubble wall does not kill. Killing implies a body that stops functioning but retains its structure for a moment. The bubble wall replaces the physics that allows structure to exist, and then the wall continues.
It does not stop. It has no mechanism for stopping. The energy difference between the false and true vacuum keeps driving it outward. Past everything you can see, past everything any human has ever seen, past everything any instrument we have built has ever detected. At the speed of light, it moves outward from its origin point forever, or until the geometry of the universe itself imposes some constraint that our current theories do not fully predict. What comes behind the wall is not emptiness. It is a universe with different rules. A region of space where different physical constants hold, where different particles are stable, where everything that existed in the false vacuum has been reconfigured into whatever the true vacuum's physics allows.
We cannot predict what that would look like. We can only say that it would be nothing like this. We do not know if this has happened. We have no instrument capable of seeing beyond our cosmic horizon, no signal that can reach us faster than light from sources outside our light cone. There is no measurement we can make, today or in any future we can imagine, that would definitively rule out the existence of a bubble already expanding in some region of space beyond our observational reach. The absence of evidence is not evidence of absence when the evidence travels at the same speed as the event. The bubble, if it exists, is already growing. We just cannot know where it started or when.
The bubble, if it exists, is already growing. We just cannot know where it started or when. But we can ask a different question. Not where it began, not when it will arrive. We can ask what happens when it does. The wall of a true vacuum bubble travels at the speed of light. Not close to the speed of light. Not nearly the speed of light. Exactly the speed of light. This is not a metaphor for something very fast. This is the literal maximum velocity permitted by the structure of space-time itself. Nothing in the universe can outrun it. No signal, no warning, no prayer. Think about what that means for a moment. Light travels roughly 300,000 kilometers every second. In 1 second, it crosses the distance from the Earth to the Moon, and then back again, and then again. The bubble wall moves exactly that fast, in every direction. Simultaneously, it does not slow as it expands. In classical physics, an expanding sphere loses energy as it grows, the energy spread across an ever larger surface. But the vacuum bubble is not a classical phenomenon. The energy driving it comes from the phase transition itself. As the bubble grows, it converts more and more false vacuum to true vacuum, releasing the energy difference between those two states. The wall is not slowing. The wall is feeding.
When the bubble wall passes through a region of space, the Higgs field at that location snaps to a new value.
Not gradually, not in stages, instantaneously. And the new value changes everything. The mass of the electron, the strength of the electromagnetic force, the precise charge that binds protons and neutrons together inside every atomic nucleus. These are not adjustable settings that can be tweaked while the machine keeps running. They are consequences of the Higgs field's value. The Higgs field is not one of many parameters in the universe. It is the parameter on which all other parameters depend. Change it, and you do not get different chemistry. You do not get exotic matter. You get no atoms at all. Coleman and DeLucia worked out the mathematics of bubble nucleation in 1980. Sidney Coleman and Frank DeLucia.
Two physicists sitting with equations that described the end of everything, in the ordinary way that physicists sit with difficult problems. Their equations, now called the Coleman-DeLucia formalism, describe how a true vacuum bubble forms and how it expands. What they found was not comforting. Once nucleated, the bubble does not pause. It does not slow. It does not wait. The geometry of space-time outside the bubble, the geometry of the false vacuum, actively encourages the bubble to grow. The energy difference between the two states, the energy released by the transition from false to true vacuum, drives the wall outward at a velocity that approaches and then reaches the speed of light.
In the Coleman-DeLucia picture, the bubble wall reaches light speed almost immediately after nucleation. Practically from the first instant of its existence, it is already moving as fast as anything in the universe is permitted to move. So the wall arrives with no warning. But what does it do when it gets here? Consider a hydrogen atom, the simplest atom in existence. A single proton at the center, a single electron held in orbit by the electromagnetic force. The electromagnetic force exists because the electron carries a charge. The electron carries that specific magnitude of charge because of the current value of the Higgs field. In the new vacuum, the Higgs field has a different value. The electron may have a different mass.
The electromagnetic coupling may have a different strength. The strong nuclear force that holds the proton together, itself dependent on the energy scale set by the Higgs mechanism, may have a completely different character. The atom does not explode. It does not collapse inward. It does not radiate its energy away. It simply ceases to be an atom in any recognizable sense, because the physics that permitted atoms to exist has been replaced. Now scale that up. Your body contains roughly 7,000 quadrillion atoms. Every covalent bond in every protein in every cell. Every hydrogen bond in every strand of DNA. Every ionic gradient across every membrane. Every action potential propagating down every nerve fiber.
All of it rests on a foundation of quantum mechanics and electromagnetism. All of quantum mechanics and electromagnetism, as we know them, rests on the Higgs field sitting at its current value. The bubble wall does not destroy your body. Destruction implies something that happens over time. A bomb takes milliseconds. A fire takes minutes. Even the most violent physical processes in nature have a duration, a beginning and an end, separated by some measurable interval. The passage of the bubble wall would take less than 10 to the power of negative 43 seconds. That is the Planck time. It is the smallest interval of time that current physics assigns any meaning to. Below that scale, the very concepts of before and after stop being well defined.
Your nervous system cannot register anything at that time scale. The fastest known signal in your body, an electrical impulse in a pain-sensing nerve, travels at roughly 100 meters per second. The bubble wall travels at 300 million meters per second. There is no version of events in which your nervous system perceives the wall. There is no moment of awareness. There is no instant of realization. This is not death. Death is a biological process with stages. Death is something that happens to organisms over time. Death leaves a body, a remnant, a thermal signature, a chemical residue. What the bubble wall enacts is something without an adequate word in any human language.
It is not even erasure, because erasure implies that something was present and is now absent. The bubble wall does not make you absent. It makes the conditions for your presence inapplicable, like asking for the location of a sound in a universe without space. The question does not have an answer. Inside the bubble, there may still be something. The true vacuum is not nothing. It is a different something, a different arrangement of field values, a different set of physical constants. Whether those constants permit any form of complexity, any structure stable enough to last longer than a Planck time, depends on details of the true vacuum that we cannot know from inside our current one. It is possible the true vacuum permits structures.
It is possible. It does not. It is possible the question is not well formed. But here is what we can say. Whatever exists inside the true vacuum bubble, it is not us. Not any version of us, not any descendant of us, not any configuration of matter that began as us. The atoms that were us were made of particles whose properties depended on our vacuum. Those particles do not carry over. The information does not survive the wall. There is a kind of strange quietness to this. Not comfort, exactly, but a certain absence of the things that usually make endings terrible. No suffering, no loss, no mourning. Because mourning requires memory, and memory requires neurons, and neurons require atoms, and atoms require physics, as it currently is.
None of those conditions hold on the other side of the wall. The end would not be experienced. It would simply occur. From the outside, from some impossible vantage point beyond physics itself, it would look like the universe had simply changed its mind about what kind of universe it wanted to be. One state, then another state. No commentary, no ceremony. No one left to mark the transition. We spend enormous effort preparing for bad endings. We have emergency services, medicine, escape routes. We have developed elaborate social and cultural systems for confronting death. Rituals, religions, philosophies. Every one of those systems assumes an ending with duration. An ending with a before and an after that are distinguishable from the perspective of those involved.
The vacuum bubble offers no such duration. There is no moment in which emergency services are relevant. There is no moment in which any system of thought about mortality applies. The transition happens below the level at which anything we call experience can occur.
And so all of our preparations, all of our philosophies, all of our rituals, none of them are addressing this particular scenario. This is the one ending for which no preparation is possible or meaningful. There is something almost clarifying about that. If there is nothing to be done, then there is nothing to be anxious about. The vacuum bubble is the one existential risk that is genuinely not worth worrying about, not because it is unlikely, but because no response is possible.
And things to which no response is possible are, in a deep sense, outside the domain of concern. They belong to the domain of simple, quiet facts about the universe. Facts to be contemplated, not feared.
We live inside a boundary we cannot cross. We did not build it. We cannot remove it. It is not made of matter or energy. It is made of causality itself. Physicists call it the light cone. Every event in space-time has one. It is the region of space and time that can, in principle, send a signal to that event, or receive one from it. Nothing moves faster than light. Therefore, nothing that happens here can affect anything beyond the outward moving surface of the light cone. And nothing that happens beyond the inward moving surface of the light cone can affect anything here. This is not a practical limitation. We are not saying we lack the technology to communicate faster than light.
We are saying the geometry of space-time makes it physically impossible, in the same way that a square circle is geometrically impossible. Not an engineering problem, but a logical one. The prohibition on faster-than-light signaling is not a rule that some future civilization might circumvent. It is embedded in the causal structure of space-time itself. Special relativity has been tested to extraordinary precision for over a century. Every test has confirmed it. The light cone is real. Now apply that to the vacuum bubble. The bubble wall travels at the speed of light. This means the bubble wall and the first signal of the bubble's existence travel at exactly the same speed.
If the bubble nucleated 1 light-year away from Earth 1 year ago, the bubble wall and the first photon it emitted are traveling toward us, side by side. They will arrive at exactly the same time. The photon will not reach us and give us a moment to prepare. The photon and the wall are the same event, seen from different perspectives. If it nucleated 10 light-years away, 10 years ago, we have been in the dark for a decade. The bubble has been growing for 10 years. It has consumed a sphere of space, 10 light-years across. Everything in that sphere is already gone, and we have received exactly 0 information about it. Not because the information is lost. Because the information is traveling at the same speed as the destruction. There is no gap. There is no interval of warning. If it nucleated 1 billion light-years away 1 billion years ago, we have been in the dark for 1 billion years. 1 billion years in which the bubble has been expanding, consuming galaxies, sterilizing clusters of space that may have contained stars, planets, chemistry. All of it replaced. And not one of those extinctions sent us any warning. Not because those places lacked the capability to signal, but because the signal and the end were the same thing, moving at the same speed, arriving at the same instant. The light cone is a prison, not a cage with bars. A cage with a rule.
The rule is that cause and effect are bounded by the speed of light. And because the vacuum bubble is itself a cause that propagates at exactly the speed of light, its effect, its arrival, cannot be preceded by any announcement of its existence. Every instrument we have ever built is a detector of the past. Every photon that reaches our telescopes is a fossil. The Hubble Space Telescope, the James Webb Space Telescope, the Event Horizon Telescope, extraordinary machines capable of resolving features we could not have imagined a generation ago. All of them are, fundamentally, very sophisticated archaeology tools. They sift through light that left its sources years ago, centuries ago, billions of years ago.
They give us an extraordinarily detailed picture of how things were. They tell us nothing about how things are. The gap between what things were and what things are is precisely the gap the vacuum bubble could occupy. The bubble could be there, right now, in a region our telescopes last observed 1 billion years ago as perfectly ordinary. The light showing us that ordinary region is 1 billion years old. The bubble could have nucleated 900 million years ago. We would not know. We cannot know. The light that would tell us has not arrived yet. And when it does arrive, it will arrive simultaneously with the wall. Consider what this means for our picture of the universe. We look at the sky. We observe galaxies.
We measure spectra and redshifts and distances. We see a universe that appears in broad strokes, calm. No obvious catastrophes in our immediate vicinity. No anomalous regions where the laws of physics appear to have changed. But all of those observations are observations of the past. The light reaching our telescopes from a galaxy 1 billion light-years away left that galaxy 1 billion years ago. We see that galaxy as it was 1 billion years ago. What is happening to that galaxy right now, in this instant, as you listen to these words? We do not know. We cannot know. The information has not reached us yet. It will not reach us for 1 billion years.
And if a vacuum bubble passed through that galaxy 999 million years ago, we would not know for another million years. And when we found out, it would be because the bubble wall was arriving, not because the news arrived early. The observable universe is not a window onto reality. It is a record of events that were close enough and old enough to have reached us. Everything else, everything beyond the boundary of our light cone, is a blank, not a mystery to be solved with better telescopes. A genuine, fundamental, physics-mandated blank. The observable universe has a radius of roughly 46 billion light-years.
Larger than the age of the universe in light travel time would suggest, because the universe has been expanding throughout the time the light was traveling. Beyond that radius, no signal has yet reached us from the present epoch. The observable universe is our entire accessible reality. But the universe itself may extend far beyond that radius. If inflation stretched the early universe by a factor of 10 to the power of 26 or more, which the standard inflationary models suggest, then the unobservable universe dwarfs the observable one by an incomprehensible margin. In that vast, dark, inaccessible region, things are happening right now that we will never know about. Galaxies are forming and dying. Stars are exploding. And possibly, vacuum bubbles are nucleating.
There is no reason to expect the rest of the universe to be like our small observable patch.
The observable patch is just the patch from which light has had time to reach us. It is a sample of convenience, not a representative sample. If the vacuum decay rate is low enough that no bubble has nucleated in our observable patch in 14 billion years, that says nothing about what is happening in the unobservable regions. We are like a person sitting in a small pool of lamplight, surrounded on all sides by darkness. The pool of lamplight tells us what it tells us. But the darkness is not empty. The darkness is simply dark. And whatever moves in the darkness moves without our knowledge, toward or away from our small circle of observation. What is happening in the dark between galaxies right now? The question has a real answer. Events are occurring out there. Physics is running its processes. Fields are fluctuating. Probabilities are being sampled. But the answer is not available to us. It is behind a wall of causality as impenetrable as the bubble wall itself, and far larger. We have been scanning the sky with radio telescopes for less than a century. We have been looking with optical telescopes for less than 500 years. The universe is approximately 14 billion years old. Our observations cover a vanishingly small fraction of cosmic history.
And they cover only the small fraction of cosmic space from which signals have reached us. The silence we hear is not evidence of safety. The silence is simply what you hear when you live inside a light cone. You hear what has arrived. You hear nothing of what has not yet arrived. And you cannot tell the difference between a universe where nothing dangerous is approaching and a universe where something is approaching exactly as fast as the news of its approach. This is the light cone prison. Not a metaphor, not a poetic way of describing our ignorance. A physical constraint derived from the structure of spacetime that places an absolute limit on what we can ever know. We built the most sensitive instruments in human history.
We have detected gravitational waves from collisions a billion light years away. We have photographed the shadow of a black hole 46 million light years distant. We have mapped the cosmic microwave background, the afterglow of the Big Bang, to a precision of a few parts in 100,000. And none of it gets us outside the light cone. All of those observations are still observations of the past. All of them still leave the present moment. The actual present, what is happening in the universe right now, completely inaccessible. We see the past. We live in the present, and the present might already contain our end. There is a thought experiment sometimes used in physics pedagogy to illustrate the strangeness of the light cone.
Imagine two observers separated by a large distance. One of them performs an experiment. The other waits. While the second observer waits, they have no information about whether the experiment has been performed. They have no information about its outcome. From their perspective, the experiment exists in a kind of superposition. Not a quantum superposition, but an informational one. It has either happened or it has not. The second observer simply does not know. Now scale that up. The vacuum bubble either exists right now, somewhere in the unobservable universe, or it does not. It is either expanding toward us, or it is not. From our perspective, both possibilities are consistent with everything we can observe. We are the second observer, waiting for information that will never arrive before the thing itself does. This is not a comforting thought, but it is an honest one. The light cone does not allow us the luxury of false certainty. It simply shows us the boundary of what we can know. And sometimes, understanding the boundary
is the most honest thing science can offer.
The number is 125.25. That is the mass of the Higgs boson, measured in giga-electron volts. Confirmed by the ATLAS and CMS collaborations at the Large Hadron Collider over the years following the boson's discovery in 2012. 125.25 giga-electron volts. A number that sounds precise. A number that, in context, is uncomfortably ambiguous. For decades before that measurement, physicists had a question they could not answer. Is the electroweak vacuum, the state the Higgs field currently occupies, stable, metastable, or unstable? Stable would mean it is at the true ground state of the theory. It cannot decay. It will never decay.
Metastable would mean it sits in a local minimum of energy. A valley on the potential energy landscape, but not the deepest valley. Given enough time or the right perturbation, it can transition to a lower state. Unstable would mean it is already decaying, just very slowly, or that it will spontaneously collapse on a timescale shorter than the current age of the universe. The answer depends almost entirely on the mass of the Higgs boson. And for 4 decades, nobody knew what that mass was. So the question sat open. Once the measurement came in, the calculation could begin, and the result was deeply uncomfortable. In 2013, Battazzo, De Grassi, Giardino, Giudice, Sala, Salvio, and Strumia published the definitive analysis.
They took the measured Higgs mass. They combined it with the best available measurements of the top quark mass and the strong coupling constant, the other 2 parameters the calculation is most sensitive to. They ran those numbers through the renormalization group equations, which track how the coupling constants of the standard model evolve as a function of energy scale. At some extremely high energy, around 10 to the power of 10 to the 11 giga-electron volts, a scale we will never probe with any conceivable collider, the quartic self-coupling of the Higgs field goes negative. When it goes negative, the Higgs potential develops a second minimum, a second deeper valley, a true vacuum lower in energy than ours. A second minimum means a second valley.
We sit in one valley. There is another valley. Between us and that other valley, there is a barrier, a hill in the potential energy landscape. The barrier is high, very high, but quantum mechanics permits particles to tunnel through barriers they classically cannot surmount. And given enough time, tunneling will occur. The question is how much time, and that depends on exactly where we sit in the potential. How high is the barrier? How wide is it? How far are we from the edge? This is where the Higgs measurement problem becomes acute. The calculation of our position in the potential is exquisitely sensitive to the input parameters. Tiny changes in the Higgs mass, the top quark mass, or the strong coupling constant shift the answer dramatically.
Not by a few percent. By orders of magnitude in the computed vacuum lifetime, by the difference between stable and metastable, by the difference between a universe that will last essentially forever and one that is running a slow countdown. The top quark is the critical uncertainty. The top quark is the heaviest known elementary particle. It interacts with the Higgs boson through quantum loop corrections. Virtual processes in which a top quark and anti-top quark briefly appear and annihilate, contributing to the effective Higgs potential. Because the top quark is so massive, these loop corrections are large. They dominate the high-energy behavior of the Higgs potential. A small change in the top quark mass translates into a significant change in the vacuum stability verdict.
How well do we know the top quark mass? Better than we knew it 20 years ago. The current world average sits around 172 giga-electron volts, but the uncertainty is on the order of 1 giga-electron volt, and that 1 giga-electron volt matters. The top quark mass is measured in two conceptually different ways at the colliders. One method reconstructs the decay products of top quark pair production and fits the kinematics to a Monte Carlo template. This gives a precise number, but it measures what is called the Monte Carlo mass, a parameter defined within a particular simulation scheme rather than a rigorously defined field, theoretic quantity.
The other method compares measured production cross-sections to perturbative QCD calculations, extracting a so-called pole mass or MS bar mass that has a cleaner theoretical definition. These methods give results that differ by approximately 1 giga-electron volt. 1 giga-electron volt that, in the context of vacuum stability, is the difference between two completely different verdicts about the fate of the universe. Isidori, Ridolfi, and Strumia investigated vacuum stability systematically beginning in 2001. In the years since, the analysis has been refined repeatedly. The honest summary is this. The current best estimate places the standard model vacuum in the metastable region, not the unstable region. If it were unstable, the vacuum would have decayed long ago, and we would not exist to discuss it.
Not the stable region. The parameters as measured point toward a false vacuum, not a true one. The metastable region. A valley that is real, but not the deepest one. A stable position, but not a permanent one. Metastable means the vacuum is like a ball resting in a bowl, on a table, near the edge of a cliff. The bowl is real. The ball is genuinely at rest in it. It will stay at rest for a very long time. An incredibly long time. A time so long that it makes the current age of the universe look like a microsecond. The estimated lifetime of the metastable electroweak vacuum, in the most careful analyses, is approximately 10 to the power of several hundred years. Not several hundred years.
10 to the power of several hundred years. The universe is currently roughly 14 billion years old. 14 billion years is approximately 10 to the power of 10 years. The vacuum lifetime estimate is 10 to the power of numbers so large that writing them out would take more space than this script. On any practical human timescale, the metastable vacuum is safe. On any astronomically relevant timescale, it may be safe. On timescales approaching infinity, it is not. But there is a deeper problem. These enormous estimated lifetimes assume that the standard model is correct at energies all the way up to the Planck scale.
They assume no new physics enters between the energies we have measured, roughly 14 tera-electron volts, and the Planck energy, which is roughly 10 to the power of 16 tera-electron volts. That is an extrapolation across 15 orders of magnitude. 15 orders of magnitude in which entirely unknown physics could appear. We have direct experimental evidence for the standard model up to roughly 10 tera-electron volts. Beyond that, we are extrapolating. We are assuming that the theory we understand continues to describe nature in regimes we have not accessed. That assumption may be correct. Or there may be new particles, new fields, new symmetries that alter the Higgs potential in ways that completely change the stability analysis. Some of those alterations would make things better.
Supersymmetry, for example. Symmetry relating bosons and fermions would add new particles to the loops that correct the Higgs potential. Those new particles could stabilize the vacuum entirely, lifting us out of the metastable region and into true stability. Other alterations could make things worse. New heavy particles that couple to the Higgs boson in the wrong way could lower the barrier height or reduce the vacuum lifetime. We do not know which. We have searched for supersymmetric particles at the LHC and found nothing. The absence of evidence is not conclusive evidence of absence, but it pushes the possibilities for new physics to higher energies further from our reach. So we are left with this, the best measurement of the Higgs mass.
The best measurement of the top quark mass. The best theoretical calculation we can perform. And an answer that is genuinely ambiguous, placing us on the boundary between safe and not safe. In a region where the error bars on our measurements and the theoretical uncertainties in our calculation are large enough to accommodate both verdicts. We built the most powerful scientific instruments ever constructed. We discovered the Higgs boson, a particle predicted in the 1960s that required a 27-kilometer ring of superconducting magnets to find. We measured its mass to a fraction of a percent. And the answer we got was probably metastable. Probably. With error bars large enough to allow for either outcome. There is a particular kind of intellectual vertigo in this.
It is not the vertigo of knowing something terrible. It is the vertigo of standing at the exact edge of what we can know, of doing everything right, every calculation, every measurement, every analysis, and still not getting a definitive answer. The universe has given us one number, 125.25 giga-electron volts. And that number sits in a region of parameter space where the answer to the most important question in physics, are we safe, is, we are not sure. There is a particular philosophical tradition that says uncertainty about large-scale fate should not change how we live. The Stoics argued that we should concern ourselves only with what is within our control and release what is not.
The vacuum stability problem sits firmly in the latter category. We cannot change the Higgs mass. We cannot alter the top quark's contribution to the loop corrections. We cannot stabilize the potential by an act of will. But the uncertainty itself is worth holding. Not for practical action, for what it reveals about the relationship between knowledge and existence. We are beings capable of asking whether our own existence is stable. We are beings capable of deriving equations that describe our own potential non-existence. We are beings capable of measuring a single number, 125.25, and recognizing that this number places us uncomfortably close to an edge. That capacity is strange.
That capacity is, in some ways, more remarkable than anything we have found in the sky. A species of primate on a small rocky planet orbiting an unremarkable star in the outer spiral arm of a galaxy among hundreds of billions, has looked deeply enough into the structure of matter to understand that its own ground might be unstable, and has done so with instruments it built, with mathematics it invented, in a project lasting barely 1 century out of the universe's 14 billion years. Whether the ground is actually unstable or not, the mathematics is silent on that question, for now. But the question has been asked, and the asking is its own kind of answer.
In the standard picture, nothing needs to trigger the vacuum decay. It happens on its own. Quantum mechanics permits something called spontaneous nucleation. A region of space can, through quantum fluctuations alone, transition to the true vacuum state without any external cause. No high-energy collision, no cosmic catastrophe, no intervention of any kind. The vacuum simply, probabilistically, tunnels. The quantum vacuum is not the peaceful emptiness the word suggests. Empty space, in quantum field theory, is not empty at all. It is a seething, roiling background of fluctuations. Virtual particle pairs appearing and annihilating on timescales too short to directly observe. Fields oscillating around their average values with amplitudes set by the uncertainty principle.
Every possible configuration of the field being sampled, with probabilities given by the path integral over all histories. In this foam of fluctuations, the probability of a true vacuum bubble nucleating in any given cubic centimeter of space in any given second is extraordinarily small. The Coleman-de Lucia formalism gives a nucleation rate per unit volume per unit time. It is an exponentially suppressed number. The exponent involves the action of the instanton, the mathematical object that describes the tunneling trajectory. And that action is very large. Large action means small tunneling probability. Very small. So small that the expected waiting time before a bubble nucleates anywhere in the observable universe is many, many orders of magnitude longer than the current age of the universe.
This should be reassuring. It is in practice not particularly reassuring, because the quantum vacuum does not consult our expectations. It samples probabilities, and a very small probability is not zero. In an infinite universe, an event with any finite probability, however small, will occur. The question is not whether it will happen. The question is whether it has already happened somewhere, and whether we are in the path of the consequences. So physicists ask, is there anything that could catalyze the process? Anything that could raise the nucleation rate above the spontaneous background? Anything that could push the Higgs field over the barrier in a specific region of space, seeding a bubble that then expands under its own momentum? One obvious candidate is high-energy particle collisions.
If you concentrate enough energy into a small enough region, you might temporarily push the local Higgs field over the barrier, separating the two vacua. This was a genuine concern raised when the Tevatron was being planned, and again when the Large Hadron Collider was being approved. Could we accidentally end the universe? The question was taken seriously. It deserved to be taken seriously. The history of physics contains several instances where new experiments opened energy regimes never before probed, and where there were initially legitimate theoretical uncertainties about what might happen. The concern about the LHC was investigated carefully by a safety assessment group, and the answer, worked through rigorously, was no. Not because the concern was confused,
but because nature has been running a far more powerful version of this experiment for billions of years. Cosmic rays, high-energy particles, protons, atomic nuclei, electrons, accelerated to extraordinary energies by supernovae, pulsars, active galactic nuclei, and processes we do not yet fully understand. These particles rain down on Earth and on every other object in the universe continuously, day and night, year after year, for the entire history of the solar system. The Large Hadron Collider accelerates protons to about 14 tera electron volts in the center of mass frame. cosmic ray events have been detected at energies above 3 × 10 to the power of 20 electron volts in the lab frame. Center of mass energies, orders of magnitude higher than anything the LHC produces.
The LHC's most energetic collisions are not the most energetic collisions that happen on Earth. They are merely the most energetic collisions we control. And crucially, cosmic rays do not just hit Earth, they hit everything. They hit the Moon, they hit Jupiter, they hit neutron stars, objects far denser than anything on Earth, objects where the collision energy is concentrated into a much smaller volume, objects where local conditions are far more extreme. They have been hitting these objects for billions of years. If high-energy collisions could trigger vacuum decay, the chance that not one of the countless neutron stars in our galaxy has triggered it in 14 billion years of bombardment is essentially zero. We are here.
Therefore, collisions do not trigger it. At least, not at the energies we are discussing. So cosmic rays are simultaneously a source of concern and a source of reassurance. They raise the stakes by showing that far more energetic collisions than anything we produce occur constantly throughout the universe. They lower the stakes by providing an empirical record of those collisions. Billions of years of data during which no decay occurred. But the cosmic ray argument has a limit. It rules out certain mechanisms. It does not rule out all mechanisms. In 2016, Nikolaos Tetradis and collaborators published a paper examining a different possible trigger: black holes.
Specifically, the formation of a black hole and the behavior of the Higgs field in the extreme curvature near its event horizon. And more specifically, the final moments of a black hole's Hawking evaporation. Stephen Hawking showed in 1974 that black holes are not completely black, they radiate thermally. As a black hole radiates, it loses mass. As it loses mass, its temperature increases, according to the Hawking formula. As its temperature increases, it radiates more intensely. The evaporation accelerates toward a final explosion, a last burst of very high energy radiation from an increasingly tiny region of spacetime. Tetradis showed that the curvature of spacetime near an evaporating black hole has a specific effect on the Higgs field configuration.
The extreme tidal forces near the singularity, combined with the high-energy radiation environment, alter the local shape of the Higgs potential. Under certain conditions, this alteration could help the Higgs field surmount the barrier between the false and true vacuum. The black hole would not just evaporate, it would seed a true vacuum bubble as it vanished. This matters because of primordial black holes. In the very early universe, density fluctuations could have caused regions to collapse directly into black holes, bypassing the stellar evolution route. These primordial black holes would have masses that depend on when they formed. Those that formed with masses below roughly 10 to the power of 15 grams would have evaporated by now, their Hawking radiation carrying away all their mass over the age of the universe. We have not directly detected primordial black holes, but various observations. Gravitational microlensing surveys, cosmic ray anomalies, distortions in the gravitational wave background place constraints on their abundance without ruling them out. They may exist. They may be evaporating throughout the universe right now. And if they are, and if Tetradis' analysis is correct, then every such evaporation
is a potential seed for a vacuum bubble. The calculation is incomplete. The full analysis requires a treatment of quantum gravity near the end of black hole evaporation, and our theories break down there.
The Planck scale is where both quantum mechanics and general relativity become necessary simultaneously, and we have no consistent theory that combines them. So the tetrades result is a suggestion, a possibility, not a confirmed prediction. There are other candidates: magnetic monopoles, hypothetical topological defects predicted by grand unified theories, could, if they exist, interact with the Higgs field in ways that locally alter the potential. Cosmic strings, another class of topological defect, could concentrate energy in filamentary regions of space. Phase transitions in the very early universe could have imprinted inhomogeneities in the Higgs field that persist today as seeds for preferential nucleation. For each of these candidates, the theoretical framework is incomplete. The Standard Model does not include gravity.
It does not account for dark matter or dark energy. It does not explain why there is more matter than antimatter in the universe. It is, by any measure, the most precise and successful theory in the history of science. And it has known gaps. Gaps where unknown physics could enter. Gaps where the vacuum stability calculation might need to be revised. Gaps where a trigger we have not yet imagined might be hiding. We have thought carefully about many possible triggers. We have ruled some out. We have found others to be possible but unconfirmed. And we know that our list of candidates is bounded by our imagination and our current theoretical framework, both of which are finite.
There is something quietly vertiginous about cataloging the ways the universe might end, not the specific mechanisms, but the fact that the list exists, the fact that the question has to be asked, the fact that we can sit here and reason carefully about high-energy collisions and black hole evaporation and quantum tunneling rates and still not arrive at a definitive answer. We have done everything right. We built the instruments. We measured the parameters. We performed the calculations. And the universe has declined to give us a clear verdict. It has handed us a number, 125.25, that sits exactly at the boundary where the answer is ambiguous.
It has permitted primordial black holes in a way that we cannot confirm or deny. It has hidden its trigger mechanisms, if it has any, in regimes we cannot reach. The most dangerous things in physics, as in life, are not the things we have measured and found wanting. They are the things we have not yet thought to look for. The mechanisms operating in corners of the theory we have not examined. The seeds germinating in regions of the universe we cannot observe. The universe does not owe us complete information. It does not wait for our understanding to catch up with its processes. It runs on its own rules, at its own pace, in its own vast and mostly silent dark.
The triggers we can rule out, cosmic rays, collider experiments, are reassuring precisely because we can rule them out. They are known. They are bounded. They fall within the domain of things we have measured and understood. What remains after we have ruled those out is a residue of unknowns. Spontaneous quantum fluctuations. Black hole evaporation in regimes our theory cannot fully describe. Physics beyond the Standard Model that may alter the Higgs potential in ways we have not calculated. Events occurring right now in regions of space-time we cannot observe. The residue is not large. The residue may not be dangerous on any timescale that matters.
cannot be eliminated by more measurements at the LHC, or better theoretical calculations within the Standard Model, or more careful surveys of the cosmic ray spectrum. It can only be eliminated by a deeper theory, one that extends beyond the Standard Model, that includes gravity, that gives us a complete picture of the Higgs potential from 0 to the Planck scale. We do not have that theory. We are working toward it. And while we work, the residue sits quietly in the background, not demanding attention, not announcing itself. Simply present, as all genuine uncertainties are, patient, silent, and indifferent to our schedules. And if it has already started, somewhere in the dark between galaxies, then everything we are discussing right now is the past.
And if it has already started, somewhere in the dark between galaxies, then everything we are discussing right now is the past.
There is a possibility we have not yet considered. Everything we have discussed, the metastability, the bubble, the light speed wall, rests on a single foundation, the Standard Model of particle physics, 17 fundamental particles, 4 fundamental forces, decades of experimental confirmation, more precise than almost anything else in the history of human science. It is the most successful theory ever constructed, and it is incomplete. The Standard Model has nothing to say about gravity at the quantum scale. It cannot incorporate the general theory of relativity, the other great pillar of modern physics, without the equations breaking down into infinities. It has no explanation for dark matter, which accounts for roughly 27% of the total mass-energy content of the universe.
Every galaxy we observe rotates as though it is embedded in an invisible halo of something that does not interact with light and does not fit into any of our 17 particle categories. Dark matter is not a fringe hypothesis. It is one of the best supported observational facts in all of cosmology. And the Standard Model cannot tell us what it is. There is also dark energy, the force or field or property of space-time itself that is causing the expansion of the universe to accelerate. We discovered this in 1998, and it earned a Nobel Prize, and we still do not know what it is. It makes up roughly 68% of everything. We have no particle for it. We have no mechanism.
We have a number that fits the data and nothing else. When physicists use the Standard Model to calculate the stability of the Higgs field, they are calculating inside a framework that already has these enormous gaps. They are working with a map that covers perhaps 5% of the territory. The stability calculation requires knowing the precise quantum corrections to the Higgs potential. These corrections come from virtual particles, particles that exist only briefly as quantum fluctuations, borrowing energy from the vacuum for fractions of a second before disappearing again. Every particle that exists contributes a correction. Known particles, known contributions, unknown particles. If there are particles we have not yet discovered, particles associated with dark matter, particles predicted by theories we have not yet developed, their contributions to the quantum corrections would change the calculation. The metastability we infer might vanish. The vacuum might be perfectly stable after all. Or the instability might be deeper than we thought. We do not know. We cannot know until we know what the missing pieces are. One of the most carefully studied extensions to the Standard Model is called supersymmetry, often shortened to SUSY. In supersymmetric theories,
Every known particle has a partner. The electron has a selectron. The quark has a squark. These partner particles have different quantum properties, and their contributions to the Higgs field corrections would stabilize it.
If supersymmetry is real, the vacuum may be entirely safe. The metastability window that the measurements of the Higgs mass suggest might be closed. Physicists have been searching for supersymmetric particles since the Large Hadron Collider began running in 2008. The LHC is the most powerful particle accelerator ever built. It accelerates protons to nearly the speed of light and smashes them together, creating conditions not seen since the first microseconds after the Big Bang. It has found nothing that looks like a supersymmetric particle. Not a hint, not a statistical excess. Nothing. This is a significant result. It rules out large portions of the supersymmetric parameter space, the range of possible masses and coupling strengths, where the partner particles could have been hiding.
Lighter supersymmetric particles, the ones that would be easiest to produce, appear not to exist at the energies the LHC can reach. They might still exist at higher energies. There are versions of supersymmetric theory that would put the partner particles beyond the reach of any accelerator we can currently build. If that is the case, we may not be able to test the theory directly for many decades. And in the meantime, the stability of the vacuum remains uncertain. There is another framework, even more ambitious and more unsettling, called string theory. In string theory, the fundamental objects of physics are not point particles, but tiny one-dimensional strings, vibrating at different frequencies to produce different particles.
The theory exists in 10 or 11 dimensions, with the extra dimensions curled up so small that we cannot detect them. String theory predicts the existence of a landscape, an almost incomprehensibly large collection of possible vacuum states, each corresponding to a different set of physical constants, different particle masses, different strengths of the fundamental forces. The estimated number of vacuums in this landscape is 10 to the power of 500. That number is not intuitive. Imagine a 1 followed by 500 zeros. There are estimated to be around 10 to the 80 atoms in the observable universe. 10 to the 500 is an almost meaningless scale by comparison. In a landscape that vast, most vacuums are unstable.
And we happen to exist in one that has lasted long enough for galaxies to form, stars to burn, planets to cool, and life to evolve. This is not surprising in hindsight, because a vacuum that decayed in the first seconds would not produce observers to notice. But it says very little about whether the vacuum we occupy is the stable kind, or the kind that will eventually fall. Perhaps we are in a genuinely stable corner of the landscape. Perhaps there is no true vacuum lower than the one we occupy, and the metastability calculation is simply wrong, an artifact of using an incomplete theory in a domain where it breaks down. Perhaps the universe will last, not 10 to the 100 years, but indefinitely.
We do not know. This is the honest answer. Not ignorance. Precision. We have measured the Higgs boson mass to 4 significant figures. We have computed the quantum corrections through multiple loops of perturbation theory. We have placed our universe on a phase diagram of vacuum stability and found it sitting near the boundary between stable and unstable. All of this is real, careful, impressive science. And it is science performed inside a framework that we know with certainty is not the complete picture. The most frightening thing about vacuum decay may not be that it is likely. It may be that we cannot yet say with confidence whether it is possible. There is a particular kind of uncertainty that is worse than knowing something is dangerous.
It is not knowing whether the danger category applies at all. A locked room may or may not contain something harmful. As long as the door is closed, you cannot prepare for either outcome. You can only wait. Physics stands outside a locked room. Behind it may be a stable universe, permanent and safe, persisting long after every star has burned out and every black hole has evaporated. Or behind it may be a timer set in the first moments of the Big Bang, counting down in a language we have not yet learned to read. We have the best instruments in human history pressed against the door. We can hear almost nothing through it. What we can say with certainty is that the question is real.
Vacuum decay is not a thought experiment or a philosophical abstraction. It is a physical possibility derived from physical measurements, grounded in the best mathematics we have. Whether it applies to our universe is a question that better physics will one day answer. We are not yet at that day.
There is a line of reasoning that might seem at first like comfort. We are here. We exist. We are thinking, breathing, conscious organisms in a universe that has sustained complex chemistry for billions of years. The fact that we exist at all is a piece of evidence. Specifically, it is evidence that vacuum decay has not yet occurred in our region of space-time. Because if it had, we would not be here. Observers can only exist in the before, never in the after. This reasoning is called the weak anthropic principle, and it is logically correct. It is also, when examined carefully, almost entirely useless as reassurance. The principle tells us about the past. It says nothing whatsoever about the future. Surviving until now is not evidence of protection.
It is evidence only of luck, or more precisely, of selection. We are, by definition, the observers who survived long enough to be observers. But the set of surviving observers does not form a random sample of all possible universes or all possible moments in time. It is a biased sample. Biased toward survival. Biased toward the before. Think of it this way. Imagine a game in which a coin is flipped once each second. If it lands on tails, the game ends immediately and the room is sealed. If you are still in the room, still participating, it means every flip so far has landed on heads. You might have been playing for minutes, for hours, for years.
The fact that you are still there tells you only that you have not yet lost. It does not change the probability of the next flip. It does not mean you will win. It does not even mean the odds are in your favor. The universe has been running for 138 billion years. By human standards, by geological standards, by almost any standard of time we have practical experience with, this is an enormous duration. Civilizations rise and fall in thousands of years. Species evolve over millions. Continents drift over hundreds of millions. 138 billion years encompasses all of that and more. But theoretical estimates of vacuum lifetimes in metastable configurations run to numbers like 10 to the power of 100 years. Or 10 to the power of 600. These numbers are so large that they have no meaningful analogy in human experience. Compared to them, 138 billion years is less than a rounding error. We are, if these estimates are correct, in the very earliest stages of the universe's potential timeline. a murder does not become impossible because it has not happened yet on the first day of the year. The anthropic argument fails in another, deeper way. It assumes that our survival is informative. But survival tells you nothing about the mechanism that allowed it.
A person can survive a car accident by luck, by skill, by the quality of the safety features in the vehicle, or by an asteroid destroying the oncoming truck 1 second before impact. Survival is consistent with all of these explanations. It does not help you identify which one applies. Similarly, our existence is consistent with the vacuum being stable. It is also consistent with the vacuum being metastable and us simply occurring early in the timeline. It is consistent with the vacuum having already decayed elsewhere and the bubble not yet reaching us. Our existence cannot distinguish between these cases. Some physicists extend the anthropic argument into the multiverse framework.
If there are an enormous number of universe regions, each with slightly different physical constants and vacuum states, then most of them will be empty. Most will have decayed within seconds, or failed to produce the conditions for matter to hold together, or collapsed under their own gravity before stars could ignite. The ones that survive long enough to produce observers are, by definition, the stable ones. We are in a survivor because we are observers. This sounds like it explains something, but it explains only why we are here, not whether we will continue to be. Existence is not a guarantee. It is a filter, and filters show you only what has already passed through. They say nothing about what comes next. Consider a shoreline. Waves have always come in.
You have lived your whole life near the water, and the shore has never collapsed. That is evidence that the shore is stable. It is not evidence that the shore is indestructible. The fact of your survival along that shore has no bearing on whether a wave is forming somewhere out at sea, too far to see, too large to stop. We are the shore. The ocean extends in every direction, in every dimension of space-time we can and cannot perceive. We have survived everything that has happened within our causal horizon. We cannot see what is forming beyond it. There is one more subtlety worth sitting with. The anthropic argument assumes that observers can only exist before a vacuum decay event. This is almost certainly true.
But it also means that every observer in every universe will always observe a pre-decay state. There is no observer who has ever seen a vacuum decay from the inside. Not because decays are rare, because the class of entities who could report on such an event does not exist. The experience is impossible by definition, which means our evidence is always and unavoidably from the safe side of the boundary. Even if every region of spacetime eventually undergoes vacuum decay, the observers within those regions would only ever report the time before. The data would always look like stability, not because the universe is stable, but because instability cannot be witnessed.
Look up at the night sky and you are seeing the past. Not metaphorically, physically. The light reaching your eyes left its sources years ago. The stars nearest to us sent their light years before it arrived. The galaxies at the edges of what telescopes can see emitted the light we detect nearly 14 billion years ago, when the universe was in its infancy. What we call the present state of the cosmos is, in reality, a layered archive of history at every scale of distance. The observable universe extends roughly 46 billion light-years in every direction. This boundary is not the edge of the universe. It is the edge of what we can, even in principle, know anything about.
Beyond this boundary, light has not had enough time since the Big Bang to reach us. Beyond this boundary, space-time continues. We have every reason to believe the universe is much larger than the observable portion, possibly infinite. But that continuation is permanently, structurally hidden from us. It is not that there is nothing there. It is that there is no mechanism by which information from there could ever arrive. This boundary is absolute. It is not a limitation of our instruments. It is a consequence of the speed of light and the age of the universe. No telescope, however powerful, no theoretical advance, however profound, can reach past it.
Causality ends there for us, in the sense that nothing beyond that line can affect us, and nothing about us can affect anything beyond it. Now consider what this means for vacuum decay. A bubble forming somewhere beyond the observable horizon would expand at the speed of light. It would grow for millions of years, billions of years, sweeping through star systems and galaxies, converting the physics of everything it touches into the physics of the true vacuum. And we would never know. Not because the bubble is quiet, not because we are not looking, but because the geometry of space-time guarantees that no information about it can reach us before the bubble itself does. If the bubble wall arrives from beyond our observable horizon, it arrives without warning.
Not the warning that we failed to detect, the warning that cannot exist. There could be dozens of such bubbles expanding right now in the regions beyond our perception, each one erasing galaxies as it expands, each one perfectly silent from our perspective. Perfect silence is what physics produces at the edge of the light cone. It is not eerie. It is not unusual. It is simply what causality looks like from the inside. But the geometry becomes even more unsettling when you consider what happens just inside the observable boundary. The galaxies we see at the farthest reaches of our instruments are showing us their state from billions of years ago.
If any of those galaxies underwent a vacuum decay event 3 billion years ago, the light from that event is still traveling toward us. We will eventually receive that information, but the bubble wall, if it formed near enough, might arrive at the same time as the warning, or before it. There is a precise way to think about this. The bubble wall travels at the speed of light. The information about the bubble's formation also travels at the speed of light. If the bubble formed very far away, the warning reaches us before the wall. We would see a sudden, unexplained change in the physics of a distant region of space, and we would have time, millions of years perhaps, to understand what was coming.
If the bubble formed close enough, the warning and the wall arrived simultaneously. We would see the anomaly in the same instant the wall arrived. There would be no gap. And if the bubble formed at just the right distance and angle, the wall could arrive before any detectable anomaly in the light we receive from that region. The geometry permits this. It is not a paradox. It is simply a consequence of the way light cones work in an expanding universe. The universe is not obligated to announce itself. In the darkness beyond our vision, in the regions of space-time we can name but never see, events are occurring right now. Stars are being born. Galaxies are colliding. Black holes are merging. sending gravitational waves through space-time that will dilute to nothing before reaching us. And perhaps, in one of those distant, invisible regions, a bubble of true vacuum has formed, is growing, is on its way. We sit in our small sphere of knowable space, and we listen, as carefully as we can, with every instrument we can build. We hear nothing unusual, no anomaly in the cosmic microwave background, no strange polarization in the light from distant quasars, no discontinuity in the physics of any region we can observe. And the silence tells us almost nothing. Silence is the default condition of a universe governed by a finite speed of information. Silence means only that nothing within our causal horizon has yet produced an anomalous signal.
It says nothing about what is happening outside the horizon. It says nothing about what happened inside the horizon long enough ago that the signal has not reached us. It says nothing about what will happen next. The observable universe is not the universe. It is a window, and windows, by definition, show you only what is on one side. On the other side, the silence is not ours to hear or not hear. It simply is, and into that silence, the physics of vacuum decay suggests bubbles can grow unannounced. There is a thought experiment physicists sometimes use. Imagine placing a detector sensitive enough to measure any anomaly in the Higgs field, anywhere in the observable universe. A perfect instrument.
One that could detect the earliest moment of bubble formation, the smallest deviation from the expected vacuum energy, anywhere within the 46 billion light-years of space we can, in principle, observe. Such a detector would be useless, not because of engineering limitations, because the bubble wall travels at exactly the speed of light. The information about the bubble's formation travels at exactly the speed of light. The detector's signal and the bubble's arrival would reach us simultaneously. The warning would not be a warning, it would be the event. We could watch the entire observable universe with perfect precision for every second of time remaining in the universe's lifespan, and we would never have more than 0 seconds of advance notice. The silence is not a clue.
It is a ceiling. Somewhere out there, in the unreachable dark, the universe may already have made its decision. If it comes, you will not see it. You will not hear it. You will not feel it approaching. There will be no tremor in the air, no shift in the light, no pressure change, no electromagnetic disturbance that arrives ahead of it. The bubble wall carries no herald. It cannot, because any signal it could send would travel at the speed of light, which is the speed the wall itself is traveling. The warning and the event are the same thing. The bubble wall is not a physical barrier in the way you might imagine. It is a surface defined by a change in the value of the Higgs field.
On one side of the surface, the field sits at its current metastable value, and the physics of our universe applies. Protons have mass, electrons have charge, atoms hold together. Chemistry is possible. On the other side, the field has settled to a lower energy state, and a different set of physical rules applies. What those rules permit, we cannot calculate. Our mathematics is written in the language of the physics we know. Crossing the surface does not take time. The surface moves at the speed of light, which is the fastest that any change in physical conditions can propagate through space. As the surface passes through a region, the field in that region transitions instantaneously from one value to the other. The word instantaneously is exact here.
There is no intermediate state, no gradual shift. One side, then the other. Your neurons fire at roughly 100 meters per second. Signals travel along nerve fibers through a combination of electrical and chemical processes, rapid by the standards of biology, but slow by the standards of physics. The bubble wall travels at approximately 300 million meters per second. By the time any electrochemical signal could begin moving within your nervous system, the bubble wall would have already passed through your entire body, through the room you are in, through the city, through the planet. The comparison is not close. There would be no experience of it, not because the experience would be too brief to notice,
but because the substrate of experience would not persist long enough to generate a signal at all. Every atom in your body would lose coherence before a single nerve impulse could begin. The concept of sensation requires a nervous system that persists through time. The concept of time, in the physics of the true vacuum, may not support the structures that nervous systems are made of. It would not be pain. Pain is information. A signal generated in one part of the body, carried along pathways, interpreted by a brain that has time to process it. None of those components would survive the transition. It would not be fear. Fear is anticipation, which requires a gap between recognizing a threat and encountering it. There is no gap.
Recognition and encounter are the same instant. There is no moment in which the mind knows what is coming, because there is no moment in which the mind exists after the information could arrive. It would not be confusion. It would not be peace. It would not be anything. From the perspective of any observer, there would be a before, and then nothing that could be called an after. The universe, however, would continue. The bubble would keep expanding, sweeping through what was once our solar system, through what was once our galaxy, through the filaments of large-scale structure that connect the galaxy clusters of the observable universe. The true vacuum would propagate outward at the speed of light. Everything it passed through would be converted into the new physics.
Whether the new physics supports any kind of complexity, whether new structures could form, given billions of years under different constants, is genuinely unknown. Some physicists speculate that the true vacuum, if it exists, might be completely simple. A state of minimum energy, with no room for the fluctuations that create particles, no possibility of bound states, no chemistry of any kind. A final equilibrium that permits nothing further. Others are less certain. The physics of the true vacuum is not something we can derive from here. We can calculate properties of the current vacuum. We cannot calculate the properties of a vacuum we have never inhabited and cannot observe. What we can say is this: whole records would be erased, not gradually.
Not by entropy in the usual sense, the slow dissolution of order into disorder over astronomical timescales, but immediately. The light that left Earth tens of thousands of years ago and is still traveling outward through space would eventually encounter the bubble wall and be processed by the new physics. Every signal ever broadcast from our planet, every radio wave, every laser communication, every whisper of electromagnetic radiation, we have ever sent into the cosmos. All of it eventually caught. The concept of a record requires stable physical structures to hold information. Stable structures require consistent physics. Consistent physics requires a stable vacuum. If the vacuum changes, the structures change. And information that cannot be held cannot persist. There would be no wreckage.
Wreckage implies that matter persists in a changed form. The new physics may not support what we call matter in any recognizable sense. There would be no ruins, because ruins require atoms, and atoms require stable binding between nuclei and electrons, and that stability depends on the values of physical constants that would no longer apply. What remains is not nothing exactly. It is a region of space-time described by different equations: clean, expanding, indifferent to what it replaced. There is a phrase that appears in the physics literature stated quietly, usually in a footnote or a concluding paragraph, when researchers reach the edge of what the calculations can say. We may already be inside the bubble's light cone. This means the event may have already occurred.
Somewhere in space-time, at some point in the past, a bubble of true vacuum may have formed. It may be expanding right now. The information about its formation travels at the speed of light. The bubble wall also travels at the speed of light. We cannot receive the information before the wall arrives. If the bubble has formed, and if the geometry is such that the wall will reach us, then from our perspective, nothing is different yet. Everything looks normal. Every measurement comes back as expected. The Higgs field appears to sit where it always has, and we are still in the before. This is not panic. It is geometry. It is the consequence of living in a universe where information has a speed limit.
We are embedded in a causal structure that prevents us from seeing past certain horizons. One of those horizons is the edge of our light cone. Another, perhaps, is the edge of our existence. We are like starlight. The photons leaving a dying star do not know the star has died. They carry the information forward at their fixed speed, passing through the dark, still coherent, still arriving at their destinations, still appearing as starlight to whoever receives them. The star that sent them may have been gone for 1,000,000 years. The light does not know. We are the light. We carry forward the information of a universe that has not yet told us what it has decided. There is something to sit with in that thought, not despair.
Not dread, something stranger and quieter than either. We exist in a universe that is not obligated to inform us of its own ending. We exist in a physics that permits destruction without warning, dissolution without announcement, an ending so fast and so complete that it cannot be experienced even by the thing being ended. We have discovered this about our universe not through mysticism, not through philosophy, but through careful measurement and careful mathematics. Through the mass of a particle, calculated to 4 decimal places, compared against a phase diagram drawn from decades of theoretical work. We built the instruments. We performed the experiment. We read the number. And the number put us near the edge of a cliff we cannot see the bottom of.
Most scientific discoveries are reassuring in a particular way. They replace mystery with explanation. They convert fear of the unknown into understanding of the known. We learned that lightning was electricity, and the fear of divine punishment became a problem of engineering. We learned that disease was biological, and the fear of invisible punishment became a problem of medicine. Vacuum decay runs in the other direction. The more precisely we have measured the universe, the more clearly we have seen that the ground beneath our physics is not guaranteed. Understanding did not dissolve the fear. It created a new and stranger one. And still, we continue. We fall asleep and wake up.
We argue about things that will not matter in a century, and love things that will not last, and build things that the universe will eventually disassemble regardless of what happens to the Higgs field. This persistence is not denial. It is not ignorance. It is something older than either, something that does not have a precise name in physics. The continuation of process in the face of every reason to consider the process contingent. Physics gives us honesty. It gives us the phase diagram and the metastability window, and the light cone geometry, and the frank acknowledgement that we cannot know, from where we stand, whether the ground beneath everything has already begun to shift. What physics cannot give us is a reason to stop.
And perhaps, in the end, the absence of that reason is its own kind of information. The laws of physics are not permanent. The constants are not guaranteed. The field that fills the universe and gives mass to every particle and determines the shape of every atom is not as stable as it looks. And yet, here, in this moment, it holds. The atoms are stable. The forces are balanced. Whatever is happening beyond our observable horizon, whatever the bubble wall is or is not doing in the unreachable dark, in this region of space-time, in this instant, the physics we know continues to apply. That is enough to think in. That is enough to wonder in.
That is enough to fall asleep inside and let the universe continue its calculations without you for a few hours. The death of physics may already be on its way. We just cannot see it yet.